We're on.
Alright, so you just saw Mr. Brown react sodium and water, and since sodium and potassium are in the same group, they should have similar properties, and this is because they have a similar valence shell of electrons with only one very active electron. So when we put the sodium in water, you notice that it reacted violently, produced a ton of gas, hydrogen gas, and so we'll see what happens when we put sodium in there. Before I do that, I just want to show you. Sodium has a little bit of a silvery, grayish color, and it's a little shiny, a little bit shinier than sodium. So I'm going to place this now in the water, and you can see that it's letting off a purple flame. It's reacted, and it was a very small piece, so it's not a very long reaction, but it reacted even a little bit more violently than sodium. Alright, so let's go to the board. I'm going to let that gas out, and describe the appearance of the potassium. So it had a little bit of a silvery gray color. Silvery gray appearance, and it was a little bit shiny, and it was a soft metal. Now, you saw that when it was in water, it created hydrogen gas just like sodium did. And it actually was reactive enough that this hydrogen gas, which is flammable, the energy given off by potassium reacting with water, was enough to actually ignite the hydrogen gas, and it ignited, producing a purple flame. Ignited the H2, producing a purple flame. Sorry, running out of space here. Alright, so now let's see what happened when we put this substance in water and see what effect it had on the pH. As you can see with sodium, it turned the indicator pink, indicating that it became a basic solution, whereas neutral water is just clear. So let's take a step back, see what happens when I add a drop of phenolphthalein to this. Since it turned pink, you can say that the solution did turn basic, just like sodium did, and you would expect that because they're in the same group on the periodic table. So, it made the solution pink, which means that it's going to be basic. And the group number, it's group 1, just like sodium. And it is an alkali metal. So, after this, you would expect a similar performance from rubidium, or similar properties, actions in water, and it would probably have the same effect on the indicator, and it's in the same group. Now I'm going to go over what happens when you put sodium in water and just describe the chemical reaction. Since potassium wants to get rid of that electron, it's going to give it to one of the water molecules, and I'm going to write water as HOH here, because it's two hydrogens and an oxygen. But what happens is it's a single replacement reaction. So the potassium will come in and basically replace one of the hydrogens in the water. So you end up with potassium hydroxide and hydrogen gas. Now, you'll notice that this equation is imbalanced because we have more hydrogens on one side than the other. So what we're going to say is that we need 2 water molecules and 2 atoms of potassium to react to make 2 potassium hydroxides and 1 molecule of hydrogen gas. This is the gas which you saw, the grayish appearance, and it's also what ignited to give the flame. The reason that it made a purple flame in this case is because of the element potassium which is in there, not because of the hydrogen gas. So this is a single replacement reaction. Potassium replaces one of the hydrogens in water, producing potassium hydroxide, which is basic, which is why the indicator turned pink, and hydrogen gas, which you observe being ignited.